I'm going to take you through all the acceleration equations that you're going to need. Okay, when we talk about a constant velocity, no acceleration, this equation works great. Average velocity equals displacement over time. That's always true. No problems there. I better go in pen here. But we can also use that in acceleration. But I'm going to say, warning, this is the most misused equation in physics because people will plug in V or V0 or something for that. This is average velocity, which isn't always shown in an acceleration problem, but I'm going to show you how to use it. Okay, what I really want you to lean on are the equations that I'm going to show you right now. First of all, we know this one. Acceleration is delta V over t, which is V minus V0 over t. Delta V just means change in. Okay, I'm going to derive an equation really quickly for you. If this is the velocity versus time graph, and there's velocity and there's time, if we want to find the displacement, we would need the area under the velocity versus time graph. Well, let's just do this for a sample V0 and a sample final volume, final velocity. Let me break that up. This is going to be V0t, and this is going to be 1/2 times V minus V0 times t. What I'm going to do is I'm going to substitute this part of the equation into there. V minus V0 is the same thing as if we multiply both sides by t, at. So this is equal to 1/2 at times t, and that's 1/2 at squared. So the area of this is V0t. This is how far the object would travel if it just went at a constant velocity. This is how much additional distance it'll travel during this time t. I should write t here. If it's speeding up. Okay, and so this gives us the first equation. We use this quite a bit. Delta x equals V0t plus 1/2 at squared. V0t plus 1/2 at squared. Once again, if the acceleration is 0, that term goes away, and you just end up with the velocity equals delta x over t, because it's a constant velocity. That means the average is that constant number. Okay, there's one. There's another one that we could derive. It goes through a lot of work. I'm not going to do it. I'm not going to derive it, but I'm just going to write it down for you. It ends up looking an awful lot like what we call the equation for kinetic energy, but V squared equals V0 squared plus 2a delta x. And I'm going to call that 1 and 2 and 3. Those three equations will get you almost everything you need in acceleration. There is another one, another form. It looks an awful lot like this. It's taking this giant rectangle and subtracting this triangle to get the delta x. And what it ends up doing is giving a delta x in terms of v and t and a and t squared. But it really doesn't come up that often. I really want you to memorize these. Memorize these three equations because they come up all the time. And you really need to master those to master one-dimensional acceleration. Now let me come back to this V average. Remember what I mentioned. For constant acceleration, which is what we deal with in this class for the most part. I'll tell you when we're not, but almost every kinematics problem will have constant acceleration. The average velocity is just the average of the initial and final. So V average is equal to V plus V0 over t. I'm sorry, I keep doing that, over 2. Okay, it's the average of those two things. Notice the difference. There's a plus, there's a minus, there's a t, there's a 2. It's a different thing. This is why it's a little dangerous. But if you can do this, if you can figure out the average velocity from this, you can use that to find delta x using that equation. But once again, warning, alert, angry face. Too many people misuse that. So you've got to go in wide awake. You've got to go in fully confident if you're ever going to use this equation in a constant acceleration problem. Okay, now let me show you how we use those in the next video.